All right. So last class, I really threw a ton of equations at you guys. And today I just want to show you how to use these equations and just emphasize the key importances of everything. So what I'll do, I think the first part of today is just do the 3D problems, and then the second half of the class do an additional problem for thermal or two. So we'll focus on the 3D stuff right now. And one of the best, a good example I think we can do for 3D is by having this block here. And if we compute a force of 8 kips, and let's say that this block is, I'm just going to go with steel. And it's got a Poisson's ratio, I'm just going to give it to you guys, of 0.30 roughly. The elastic modulus is 29,000 KSI. And let's say it has dimensions of around 8 inches, 4 inches, and then 2 inches. Now, to kind of go back to this concept of this lateral strain here, this lateral strain for this problem in a rectangular configuration, let's assign a coordinate system. We'll say that this is x direction, y direction, and z direction. And let's just define what epsilon L would be. So, firstly, in which direction is normal stress and strain going to be occurring? X, y, or z? You push down on it, and you wanted to calculate a normal stress. In which direction is that normal stress going to be occurring? In the x direction, y direction, or z direction? It's in the y direction. So, the y direction is your normal sigma and your normal epsilon. What this means is in the x and z direction, we'll have a potential lateral stress, but for the sake of this problem, the lateral stress, it's just going to be an open block, so it's open on all sides, so there's no stress felt on the sides. So the lateral stress here is going to be 0. And then the lateral strain is going to be times epsilon. And this lateral strain, we can break it up as, or identify it as x and y parts, right? Because the lateral strain is going to be occurring in both the x and the z directions. You guys agree with me on that? So, instead of writing epsilon L, we can just simply write epsilon x is equal to negative nu times epsilon. I'm going to clarify up here that this is epsilon y. The y just indicates the direction that the normal strain is occurring. And then the stress is just going to be sigma y. Everyone understand what I just did there? I just added little letters towards the bottom of it just to clarify the direction that it's going. So we can just say that the strain in the x direction is equal to the negative Poisson's ratio times the normal strain, which we said was y. Any questions about that? All right. Similarly, for the z direction, it's going to be negative Poisson's ratio again, times the strain in which direction?
Is it X?
Nope. What's the direction of normal strain?
Oh,
Y.
Y.
So, let's calculate that really quickly. Step 1 is always just going to be your normal components, so whatever's in the normal. So we could calculate a stress, which we know is going to be a stress in the y direction. What would that stress be equal to? Not everyone at once. What is it? What's the area, though? How do you get that? Exactly. So it's the 8 kips divided by 2 inches times 4 inches, which is just going to conveniently give us 1 kips per square inch, KSI. Now, if we wanted a normal strain, which is the strain in the y direction, how would we calculate that? Joseph. Come on. What are our equations for normal strain?
Changing line over the original.
Right? What's another way of writing it?
Stress over strain. Oh, wait,
Well, the elastic modulus is equal to stress over strain, but you can rewrite that to then be what?
delta equals NL over dA.
Not quite. There's another way to rewrite it. So all of those equations that I gave you in the office hours, we were writing equations. Yes?
The stress over the elasticity?
Yes. You can rewrite this to say stress over the elastic modulus. So it's just going to be 1 KSI over 29,000 KSI, which is going to give you a really small number of around, 0.0000345. Now, if we wanted to calculate how much this bar deforms in the normal direction, delta, we could again label this as delta y, just to indicate the deformation in whatever direction. How would we do that? What would the equation be? You can use PL over EA. What's another equation? I would personally do the strain in the y direction times the length in the y direction. But you can do NL over EA if you wanted to. So you just multiply that strain. What was the length in the y direction? It's 8 inches. So you just take that strain that you computed right there and just multiply it by 8 inches. And what we get is still a very small deformation of 0.0000328 inches. It's a very small deformation. And then we just pretty much solved for everything that we could for the normal, right? This was everything we just did was like the very first few weeks of class. You guys agree with me on that? The next step now is if we wanted to find the lateral strains, step 2, lateral. The way we find the lateral strains is going to be epsilon x is equal to negative Poisson's ratio times what? Epsilon y, right? We wrote it right there. So the strain that develops in the x direction is going to be negative 0.30 times the strain in the y direction was 0.0000345. And what we get is negative 1.035 times 10 to the negative 5. I'm going to write it a different way. Yeah, I'm going to rewrite it slightly differently. Negative 0.0000104. But I want to show you guys something really quickly. Let's pay close attention to the direction that this force is going, because this is going to affect all of our numbers moving forward. In which direction is that force going? Is it tension or compression? Compression. So our force should really be negative 8 kips, right? So we need to make that change towards the beginning, which then is just going to carry out through everything, which means all of our answers in normal were negative. So when we then throw the negative sign into there, you guys notice the two negatives cancel, which is going to give us a positive number. And that's what that negative sign is supposed to indicate. If you were to squeeze a material by pushing it downwards, the natural response of said material is then to expand outwards. You guys would agree with me on that? It's like if you had a water bottle and you pushed it down and you can crush it, it'll just pop out slightly. It's just on a much less noticeable scale. We can do the same thing for epsilon y. But one thing you guys will notice here is what? What do you guys notice about the equations? They're the same. So we don't really need to decipher between x and z. We could just keep it as epsilon L, because the lateral strain is just the lateral strain, and it doesn't matter which direction, as long as that direction is in the direction in which it's going to be expanding or contracting with respect to compression or tension, respectively. Does that make sense? So epsilon y is just going to equal epsilon x. But here's where it gets a little tricky and why the direction matters. If we wanted to calculate the deformation in the x direction, what would the equation be that we would use? Yes.
Why is it not z equals x?
You're right. That's a typo. Or righto, I guess. I'm just so used to working in a two-dimensional plane where it's only x and y. What about the deformation in the x direction? What is the equation we can use to find that? What do we do for the normal? Strain times length. So we can use epsilon x multiplied by Lx. What you guys will notice is that the strain in both the x and z direction are the same because that lateral strain is direction independent. It doesn't matter. But the length in which that strain occurs does matter and is directionally dependent. So what is the length in the x direction? 2 inches. So you take that strain that we computed way up here and multiply it by 2 inches. And what we should get is 0.0000207 inches. I really should have specified a much larger force because we are not really doing anything to the member. What about the deformation in the z direction? What do you guys think? Yes.
The 4 inches.
Yeah, so it's just going to be epsilon z times LZ. Again, that strain is the same. Multiply it by 4 inches. And you should get 0.0000414 inches. Does that make sense to everyone? All right. Now, one of the things that we can do is if we were interested in finding an area change or a volume change, we can first find all of the final values of the lengths, widths, and heights of the block. I'm actually going to do it. I was going to change the values, but you're just going to have to bear with all of the decimal values. Sorry about that. So let's say we wanted to find the final value or the final length, width, and height. I'm going to specify those with Lx prime, Ly prime, Lz prime. The primes just indicate after a change has occurred. The final lengths, you guys would agree with me, would be in the x direction, would be the original length in the x direction, which was 2 inches, plus that delta x. Would you guys agree with me on that? Which is going to be, again, a very small value, 2.0000207 inches. In the y direction would be 8 inches plus negative 0.00028 inches. The negative came from the negative value that we had up here because we specified it was in compression, which gives us 7.99972 inches. And then in the z direction, 4 inches plus 0.0000414 inches, which gives us 4.0000414 inches. you guys would agree with me that we can now calculate whatever the volume was of the block, right? So we can say the final volume of the block is just going to be the multiplication of the 3, right? So you guys just do that really quickly, and then just tell me what you guys end up getting for that volume. Yeah. 999,085. Yeah, I'm just going to end it at 0.0. Yeah. What are the units of volume?
Inches cubed.
Inches cubed. Now, just for comparison purposes, let's calculate what the initial volume was. What would the initial volume be? Which means that we actually underwent a volume change of around negative 0.000915 inches cubed. We lost volume from the compression. It's a very small volume, but if I had chosen larger parameters, the volume difference would be much more noticeable. Now, why am I showing you this? The reason being is because last class I specified an equation right here without really giving you too much information as to what it did. So let's take that equation and now just calculate the change in volume. We had the initial V naught value, or the original volume, which we said was 64 inches cubed. The only thing now we need is epsilon x plus epsilon y plus epsilon z, or the summation of all 3 of the strains. Epsilon x, we said, was 0.00000104. Epsilon y was the negative 0.00028 plus epsilon z, which again was 0.0000104. This simplifies down to the negative 0.00028 plus 2 times 0.0000104, which is the same as that bottom equation down there. You guys see why the lateral strain is being multiplied by 2? It's because the strains in this problem, x and z, are the same, because the lateral strains are direction independent. It doesn't matter which direction they are, the lateral strain is going to be the lateral strain.
What would happen to the strain if you had something, like say it's like a piece of square tubing and you would reinforce it back with a plate? Now, it would be more bulging towards the front of it, like, what would that alter? Maybe not like, never mind, don't worry about it.
What do you mean?
It's a,
What, like a filled pipe?
yeah, so say you have like something like just a chunk of metal that's consistent throughout, right?
Yeah.
You know how you push down and it spreads out evenly. Now, what would happen when you would reinforce one side with like a backing to it? Like, would any of this, like, would the approach be any different, or would it just be the same thing?
For the volumetric change?
Because, like, I don't know. Never mind. It's okay.
No, it's an important question. Yes. The approach would generally be the same, but you would need to consider some variation in the stiffness. So you would really need to determine what the forces are in each composite, which we will learn about next week. And then you would treat each material as a separate material with the condition that now there's kind of a boundary separating the two, which now generates stress. In a lot of cases, when you're dealing with composites, usually the material is so strong that you're not really worrying about that volumetric change. Kind of like this problem, if you're dealing with steel, you can kind of see why the variation in change is negligent, you know? But if you're dealing with a very soft material, like a bearing pad on a bridge for beams, that material is designed to expand accordingly because of the fact that it's supposed to be soft to provide relaxation on the amount of force that's, or the amount of stress that's provided on the concrete. It's just supposed to distribute the force more evenly, and the only way it can do that is if it's expanding under load, just like this. Make sense?
Yeah.
So, what do you guys get for the summation of that strain? Yeah, just like that. Now, if we were to calculate the final volume, we take that 64 inches cubed and we multiply it by that value there. And what you should get, assuming no round off error, is going to be exactly 0.000915 inches cubed. If you guys plugged it into your calculator, there would probably be some round off error because we did some rounding. But in theory, this volume and that volume, using both procedures, will be identical. And that's the reason why I wanted to show you guys that equation too. I just kind of rushed over it, which I shouldn't have. Does everyone understand that? All right. Now let's do another quick example. And this time it's a cylinder. The cylinder is going to be I'm awful at sketching, so please don't mind my atrocious artwork. This is why I did not become an architect. All right. Let's say that this has a diameter of 2 inches and a height of 12 inches. No. Well, diameter of 6 inches and a height of 12 inches. And then we're going to say that this is like a concrete sample. So the elastic modulus for this concrete is going to be 3,600 KSI. One of the things that you guys will notice in your packets is there's no modulus of rigidity for concrete, and that's because concrete is generally pretty weak in shearing also. Like in actual concrete design, it's a function of the square root of the compressive strength, so it's like very weak. but the Poisson's ratio for concrete, this is a good thing to note, is generally specified in codes to be around 0.20. Now, the last thing is I want to give you guys a force of around 10 kips. All right, so really quickly, let's first, step one. What's step one of any of these 3D problems? Normal. All right. What would the normal stress and normal strain be? And let's say, again, that this is X, this is Y, this is Z. Just take a few minutes to do that for me. You know what? Matter of fact, I'll let you guys work on finding the lateral change in diameter. What is the change in diameter that the cylinder undergoes? I'll give you guys a few minutes while I'm printing out some stuff. Feel free to work on it together too. Yep. Who here's got it? Anyone yet? Olivia's got it. Anyone else? Oh, an important thing I forgot to add. When it came to that schedule change, any homework that still pertains to the exam, you guys will have a slightly less time to work on that homework now because I want to have you guys I want to force you guys to work on the homeworks before your exams. So, right before the exams, the homeworks that are due that week of generally are now due the Tuesday before the exams. So, for example, previously, homework 6, which would have been the column buckling, which would have been on your exam, was technically due after the exam. But now, since I, changed the topic, I'm kind of like shifting the homework to be due earlier. You guys still have the weekend to be able to work on the homework, but it's due before the exam, just to force you guys to do practice problems for the exam.
Can you take a picture of your updated schedule?
I'll upload it on Workspace. Yeah. Is everyone all right with that though?
Yeah, that's fine.
All right. Olivia's got it. Who else has got it? Anyone else? John's got it. I'm waiting for one more person. I'm slowly figuring out who the future engineers of this class are. And I'm trying to figure out which ones to actually try and successfully convince. Yeah, the student, remember when I said that the student got 180 or whatever in his class? I tried convincing him to go into engineering. He said absolutely not. He just loved architecture too much.
Well, I can kind of see the architecture over here. If you like to be more creative, I can get it.
Yeah, but you could be creative with engineering too.
Oh, well, crunching numbers, I feel like there's more deadlines versus creating houses on the water, you know what I'm saying? That's a little different.
You need a structural engineer for everything. How do you think structural engineers make the buildings look nice?
Yeah, but that's not the fun
All
part.
of them go bald.
All of them go
One
bald.
of them bald.
That's actually not false. Every single one of my bosses is bald.
I think there's a
That's
clear
concerning
correlation.
now because I don't want to go bald.
Well, it looks like you're gonna go bald.
Oh,
I
shit.
think you,
But then again, my close friend, his name is Ken. He's been an architect for 20-something years. He's bald.
That's 20 years. You have 10 years.
True. So, the balding rate is higher for engineering than architecture, I guess. And then there's Joe over there, the tech teacher, right? That's what you wanted to do?
Yeah, we'll
Yeah.
see what happens.
I wonder what the balding rate for that is.
You know, every shop teacher I know is 50-50.
He's quite apparently receiving. How was it?
It's alright, like, in our head.
All right. Who here thinks they have the change in diameter I want to hear some of your answers. Olivia, what did you get for the change in diameter?
Negative 0.000000164.
Negative 0.00000.
5 zeros and 164.
Okay, so again, I made the numbers way too weird, but the principle is there. All right. Who else? John, what did you get?
I'm redoing it right now, actually. Sorry.
All right. Who else has a submission answer? Almost? All right. Well, in the meantime, while you're crunching those numbers, let's get the normal stress and normal strain. What did you guys get for those? Did you get a normal stress and normal strain?
I did.
All right.
It's right though.
What did you get?
For the stress, I got 28.27 KSI.
Who else got that? 28.27?
Don't you do 10 kips over area?
That's the area, like,
10 over.
about 0.35.
Yeah. So the stress is just going to be the force over the area.
I think I used the wrong.
So it's going to be the 10 kips, positive because it's in tension, divided by the area, which was pi over 4 times 6 inches squared, which will give you roughly 0.354
Oh, I pressed the
KSI. For the strain, you take that divided by the 3600 for the elastic modulus. And you should get 0.00009,842. Any units? Oh, 2.4. All right. How did you calculate the change in diameter?
I found the change in the y first, so I took that number and I multiplied it by 12 inches.
All right. And what did you get for that answer?
5 zeros, 819.
Five zeros? There's that divided by 3600, which gives you 9824. And then you multiply that by 12.
It's basically 1 zero less than the number I used.
I got 0.0111788 inches.
Yeah, that's what I got.
That's what you all got?
Yeah.
All right. How did you calculate the change in diameter?
Multiply it by the negative mu,
Multiply what by the negative mu?
that number.
The delta y? You're saying that number. I'm not. I can't see. Epsilon y. I don't need to write epsilon x and epsilon z because, again, it's the lateral strain is going to be for both x and z, so you don't need to decipher between the two. And then epsilon y was that. And what did we get? We got negative 0.00000. One, two, three. Less 1 0. 1965.
So when it gives us, like, on our calculation, does e to like the negative whatever power?
That's just times 10 to the negative power.
Yeah,
It's
so-
just finding a way to remove all of the...
Is there an easy way in our heads to just note how many zeros we put in front?
No, because I'm having a trouble time right now.
I
So
would, like, type in all the numbers in my phone, and that's how I get this.
I'm just trying to avoid that so that you guys aren't there like, what are you doing? 10 to the negative, 10 to this, you know? So, all right. Now, what was the change in diameter equal to? This was the trick question. Which dimension are you using for L?
For the diameter?
Yeah, what is the lateral change in diameter? What is the lateral length?
6 inches.
6 inches. So, if you wanted to find the change in length or the change in diameter, it's just going to be the change in the lateral dimension. If you wanted to find the change in radius, it would just be 3 inches instead of 6. So, you take that epsilon L, multiply it by LL, and what we get is negative 0.0001788. Is that what I get? I'm trying to figure that out. 0.2 times 6. Nope. Less a 0.
It looks like it's just 1 less 0 than what's to the negative power of.
Yeah.
I think that's the trick.
Well, it's not as always as simple as that. It's just when with these small numbers, it's just very weird. But if I give you guys problems like this, the numbers will be more appropriate. It's just I'm coming up with the problems off my head. All right, I'll give you guys a few minute break. Let's reconvene at like 7. What time is it? 7:05. So let's reconvene at like 7:10, 7:11. 7:11. Not sponsored.
So the delta L, that denotes the change in diameter?
Yeah.
Okay.
Because in this type of problem, the only lateral dimension that there is the diameter, you know? Because like X or Z, it's the same dimension no matter what,
Okay.
you know?
That's just what I was confused on, because I didn't know that, I did solve for that, and I got what you got, but I didn't know if there was extra,
Yeah, if you did delta X, delta Z, it would have been the same thing, but then you're calculating it in like a particular direction, which for a circle, it's like, it doesn't even really matter.
But for like the previous question, you would have to do separate.
Yeah, because there's 3 faces.
Okay.
In this case, there's only 2, so you have a lateral and a normal.
Okay.
Yeah.
So for this, the strain and the deformation would be the same for X and Z?
Mm-hmm.
Okay.
Yeah, it's just because it's a diameter, the X and Z are they're identical.
But if it was rectangular with different dimensions, you'd have to.
Yeah.
Okay.
If it was rectangular with the same dimensions, then same principle, it would be the same. You guys feel more comfortable with the topic now?
With this, for sure, yeah.
Last week I kind of rushed through it.
The 3D, I was looking at it when I got home. I had no idea what I was looking at. But yeah, it's definitely clicking now.
Mm-hmm.
Would there be any other like three-dimensional shapes, or just really like rectangular prism and?
Only rectangular and circular. I can't be bothered. And besides, circular and rectangular are the most common ones for soft materials.
What type of sandwich did you bring?
Ham and cheese.
I like Italian sandwiches the best.
Oh yeah? Well, this is Costco ham, and it's the only thing I got, so. And you brought a snack too this time. You said you would last class.
I brought chocolate. It's
Oh.
not a healthy snack.
My first semester teaching, this one girl in my class, she went to Greece for I think like 2 weeks, and she brought me back liquor. She was like, "I think you need this," and I was like, "Why?" And she was like, "Because you have to deal with us." I felt so bad.
Liquor or licorice?
Liquor, like
Oh.
alcohol. She got it from Greece. I was like, I don't even drink, so.
Was it good? Or you didn't drink it?
Mm-mm.
So you
It's
drink
still in my room. It's like a year and a half old.
You should bring it in for after our exams.
You prefer research than me.
I'm gonna wait for a day where the class is just unbelievably not paying attention and just don't understand a single thing. Yeah, there's times where I see like students writing entirely incorrect units for measurements. Those are times where I wish I drank it.
That's definitely me.
I know, you wrote a dimension in pounds, that aggravated me.
Hey, but now I know.
I was like, you can at least guess on a dimension, since it is a dimension.
Reported for no reason. That could have just been a secret between you two.
I have to know this.
Well, hopefully we clarified that during office hours. I got an interesting problem. And by interesting, I mean you guys will probably hate it. But it's going to be fun for me to watch you guys. It's going to build on both of the things that we worked on. last class. No, I don't want to do that yet. I'll cover that at a later date. What I could do instead. Let me make the numbers realistic. Um, All right. Now we have a problem with three stresses acting on it. The reason I wanted to show you guys this was because everything that we've been doing is one-dimensional. Now, these equations, which we wrote last class, is as if we solved for each force independently and computed the lateral deformations of each, lateral strains of each, and then just summed everything together. So, for example, in the previous thing that we were dealing with, we had sigma x 1 over e, which is the strain in the x direction, right? And then there was no lateral stresses applied. Now, if you were to consider the lateral stresses only, right, then it would just be a lateral strain. So it's just a summation of all three stresses. So I guess a good way of explaining it would be if we looked at those equations and then we wanted to determine the normal stress, the normal strain, lateral strain, then we would just use the 75 kips independently, and we can calculate the lateral strains for that 75 kip force, right? Does that make sense? Well, we could also do the same thing for the 25 kip force and calculate the lateral strains, and then do the same thing for the 50 kip force and compute the lateral strains. And all of that could be independent answers, right? But those equations that I gave you If you didn't write them down, I'm going to let you guys write them down right now. Those are the ones right here. This is as if we just added the results of all three forces independently into one different thing. It's a simple plug and chug problem at this point. Does that make sense? Are there any questions about the use of these equations? You would just follow a very similar procedure. Just now, instead of just for the strain in the normal direction, right, there is not necessarily a normal direction anymore. Everything is split up between their independent directions, and you just have to decipher which one is sigma x, which one is sigma y, which one is sigma z. So I think these problems are actually a bit easier now because of the fact that you can just plug and chug. And you can use these equations for the previous two problems. So, for example, for the previous problem that we just worked on, the concrete cylinder, what was the normal stress that we had? Was it sigma x, sigma y, or sigma z?
Sigma 1.
Sigma y, which means that this was the normal direction. But we didn't have any forces in the lateral direction applied, right? No. So you can just neglect that and that. I'll come over here. That and that would just be, that's your normal, epsilon y. Then you wanted to find the strains in the x and z direction, right? For the rectangular block. Was there any stress in the x direction for the those strains? Yes or no? No. So I just had to think about it for a second. Do you guys see where those equations are coming from? They're identical to the ones that we just had. The blue represents our normal, right? So our normal force would just be epsilon y is equal to the stress in the y direction divided by the elastic modulus. And then from there, we would jump over to the red and calculate the lateral strains, which is just going to be whatever the strain was in the y direction. But this time it's just expressed as sigma y over e, which is just the same as epsilon y, but just multiplied by Poisson's ratio. You guys see where I'm going with this? It's just now everything is just kind of expanded into a plug and chug scenario. Where's the eraser? So, what I want you guys to do is take a few minutes and calculate the strains felt in all three directions. So I'll write that right here. And then you guys need a coordinate plane. I'm going to say X, Y, and Z. That's just what I like to deal with. Just keep in mind when you're solving these problems, these don't always have to be X, Y, and Z.
question about, like setting it up.
Mm-hmm.
Are any of them supposed to be negative for, like sigma? Because once I do the strain, it comes out as negative for, strain in the x direction, but it's pointing down.
That's the interesting thing is a lot of these stresses, they all just combine. So I'll help you guys out with the stress directions. All right, we take a look at our coordinate plane. We have sigma x. Which direction is sigma? Which force, first of all, is sigma x?
25
25
kips.
kips
Negative 25 kips.
divided by 60 inches squared. Sigma y. Which one's sigma y?
75.
Positive or negative?
Positive. There's negative.
Negative. Divided by 24. And then sigma z is what?
50.
Positive or negative?
Would that one be negative?
It's also negative.
Okay. All right. Then that's where I made my mistake.
Divided by 40. Yeah, it's important to understand whether the stress is causing a compression or a tension stress on the body. three-dimensional equations. Do you need them on the board? Use those 3D equations. Otherwise, you're gonna have to solve each and every single deformation for each load independently, which is gonna take you about an hour to do. It'll take me about 30 minutes to do.
It was just the normal stress strain one that you had, those three, right? That one that you were scribbling on, that's you.
Yeah, the ones that I was scribbling on, and the only reason I was scribbling on them is just to show you guys how they can relate to uniaxial loading, which is what we were doing previously the past hour.
Okay, just wanna make sure.
Yeah. No idea.
That makes it.
Well, I think you took the strain and then multiplied by that.
Looks like yes, you're off by another zero.
The strain of each.
17,000 KSI.
You find this else for each one.
There's,
And then-
it's kind of hard to see. I don't fault you for that. You can just,
No, I'll do that.
all right. I think all of your answers are just going to be
An extra.
divided by 10.
Yeah, divide by 10.
Yeah.
We'll just do that then.
Yeah, and you just do that for each one.
Yeah, yeah, strain.
That's all we need?
That's what it.
Oh, shit.
Yeah.
I was trying to do everything else too.
You don't need to find the extra deformations, but if you wanted to, you just multiply the strains by their corresponding lengths.
Okay.
I'm not asking you guys to find the volume change, just
Oh,
the strains. Because we already did examples showing how you guys do
That's
them.
I was trying to do.
If you wanna pin it back, so it's that one number.
Yeah.
No, no, this is great, right?
No, I didn't.
Everyone got answers? Or not yet?
But like, it's not gonna be in decimal form, it's gonna be the other way.
In the,
Wherever it's the number times 10 to whatever power.
that's fine. I prefer it that way. I just write it out with all the decimals because some of you, I think, get confused by it.
We can use that, that's fine, because it's easier to do.
Yeah, if you want to do it that way.
I don't know how to do
Just don't be writing e to the negative
that.
4.
No, no.
That aggravates me if I see that.
Oh, it's 100
No. That's minus 500 points.
500?
Yeah, 500 points. You have to make up 5 assignments for it.
Maybe we should solve engineering that.
This has a stress of negative 0.42 KSI. 75 over 24 was negative 3.13 KSI. And then 50 over 40 was negative 1.25 KSI. Everyone got that, right? The stresses?
Yeah.
All right. To find epsilon x, epsilon y, and epsilon z, it is just as simple as plugging and chugging. So, what was the equation? I gotta. This is like one of those things where it's like I can't.
I forgot to.
Here we go. All right. So, 1 over 17,000 KSI times sigma x, which is negative 0.42, minus 0.30 times negative 3.13 minus 0.30 times negative 1.25. Did everyone get that for the equation? For the strain in the x direction? What did you do, Nicole? but I do. What did you do? Were you like trying to, I guess, find it for each force independently?
No, I think when you were over here, you said that you would do the 3D. But then
You were basically solving.
I put stress over the heat.
That's what I did.
You did, but I gave you guys those equations because what you're doing here is technically correct, but then you would need to do it for each force independently. Whereas the equations that I gave you with the sigma x minus mu sigma y minus mu sigma z accounts for everything independently, all added
So
together.
is this correct either way?
It is, but you're gonna take the rest of the class trying to solve that.
So what, so if you did all those three for each for each one,
If you did
it's the same as just doing this one.
if you did the procedure for each force independently, calculated the lateral strains for each one, and accounted for the directions correctly, it's the same as plugging and chugging here.
Okay. I'm gonna write this
Yes.
down, or I just wanna
I'll
see
write
it.
it down.
Right, so you guys got this, or some of you did, others not so much. What did you guys get for the strain?
5.26 times 10 to the negative fifth, or 5.27.
And that was negative or positive?
1 over e numbers.
Positive.
Oh,
What do you guys notice? It's a positive value.
You just cross out.
It might seem counterintuitive, but if you think about it, the compression of this force is very large. It's 3 times the size of this, which means it's going to want to push that outwards. The compression of this is very large also, which is also going to want to push that outwards. This force is only about a third of this force and a half of this force, which means that the total force needed to push it back in would probably need to be larger than both 75 and 50 kips, which is why, when we calculated it, we still got a positive strain. It's very confusing because everything is a compressive force, but if you were to think about it like this, like 2 people pushing against each other, a larger person would be able to push the other person more easily, right? That's exactly what's going on here. These are like larger forces, so they're pushing on this more easily than this is pushing on that. So there's less resistance. The 25 kips is basically resisting any lateral deformation. What did we get for epsilon y? You do 1 over 17,000 KSI times sigma y was negative 3.13 minus 0.30 times sigma x, which was negative 0.42, minus 0.30 times negative 1.25. And what did we get for this?
Negative 1.54 times 10 to the negative fourth.
I would expect that to definitely be negative because that is the largest force presented and the smallest area. So it's the largest stress, which means largest deformation will likely occur there. That's going to be the governing compression. So if you were to get something like tension, that would be concerning. And what about epsilon z? You just throw that as 1 over 17,000 KSI times negative 1.25 minus 0.30 times negative 0.42 minus 0.30 times negative 1.25. And the strain for that was what?
This one I also got negative. Is that wrong? Or
If that's what you got and whatever other people got, then it must be correct.
all right, I got negative 1.102 times 10 to the negative fifth.
That seems reasonable because, again, it's a 50 kip force. So most of the lateral expansion outwards is going to be occurring in that direction, meaning it means. And then the greatest lateral compression is going to be on the top. And then this just happens to be resisting any lateral compression or lateral expansion from this force. So most of the lateral redirection is being directed that way because this is the path of least resistance. You can think of it.
Okay.
Does that make sense to everyone? Basically, just plug and chug the numbers, and as long as you do it right, the results will make sense, right? You might seem like they don't, but as long as your numbers are all correct, they'll work perfectly fine. All right. And then there's enough time for, I think, one more problem before I give you guys your get out of jails. And I'm going to give you guys about 5 minutes, 10 minutes to work on it. You should hopefully be able to get it done. Let's say that this is an A36 steel sample. A36 steel. It's about 24 inches in length. And it's subjected to a temperature change of 100 degrees Fahrenheit. If its cross-section is 1 inch by 1 inch, knowing that E is equal to 29,000 KSI and mu is equal to 0.30, find epsilon x, epsilon y, epsilon z, no. Find epsilon y and epsilon z. And just for clarity on what those are, if that's your coordinate plane, this is going to be y, and that's going to be z. Now I just combined two problems into one. Wow. Oh boy. And then I'll be nice and I'll give you guys alpha also. That's 6.5 times 10 to the negative 6, 1 over degrees Fahrenheit. Oh yeah, Thomas, did you watch the lecture at
I
all?
watched the first, 45 minutes, I didn't finish it.
Okay, so you saw coefficient of thermal expansion then at least, right?
I saw it, did I grasp it all?
I think everyone kind of grasped thermal a little bit better than lateral strains. Would I be correct in that assumption? All right, so you guys should be able to find the stress without issue.
Yeah, is it supposed to be no force here or what?
It's restrained on both sides and subjected to a temperature increase. What does that tell you?
It's gonna be pushing against the wall.
It's going to be pushing against the wall, which is going to generate what? You need to compute the force in the bar due to the temperature change. We did this with the rail problem last class. The only difference now is I'm asking you guys to find the lateral strains due to the temperature increase.
So you need to find,
Your first step is to find
lowercase
the...
delta, right?
What?
You have to find lowercase delta t first.
Basically, yeah. You need to find the required deformation that would occur if it was unrestrained.
And then you would find the
the force that would cause that same deformation, and then you know that that force is what, in tension or compression?
Well, in this case, it would be, compression, right?
Yeah. You got it?
Oh, I'm gonna go back right now. We don't use,
You don't what?
use that right?
Yeah.
Or no?
Yeah. That's, cause this was a limit of my work.
Just look at A and B on your get out of jail. It's a copy paste.
Okay, so we
Kinda.
do this, or we use G.
I think it was just.
No, I gave you guys the Python radio.
Oh.
Yeah, okay.
So I canceled that.
Yeah, these are your equations, except the only thing is I gave you guys delta T, so you just, first of all,
So we
need to
just do this.
just use that equation.
That was not what that was the rest of the.
Of steel.
This was a balloon. So steel for 836
And everyone knows that I upload the solutions to the get out of jails, right? Everyone sees those?
I
Okay.
feel like I never used the word, I'm not like an idiot.
I post them for a reason. I
No, I
initially
know.
wasn't going to, but then after the first, but right before the first exam, I was like, let me do that.
Yeah. Oh, not a bad idea. I just know. Okay.
All I ask is that you don't share those with anyone. The reason being is because I want to reuse them next year or next semester, and it makes it harder for me to reuse them if the answers are already out.
Once the class is done, bro, we're locked out.
What?
That's what it is. I said, once the class is over, I said, we're locked out. That's what it is.
Yes.
So if it was in compression, it would be negative then?
Yes.
Even though I didn't get a
Yeah,
negative
so I
answer?
saw, I'm assuming that if you put in.
The thing is, when it comes to temperature, when you're going over, it's this thing called compatibility. We go a lot more into detail with it for statically indeterminate members, but basically, it's kind of like saying that delta, which is the deformation due to the temperature change, plus delta F, I'll call it, that's the deformation due to the force.
Yeah.
If you do it in this one also.
Those are both calculating the deformation at here. So actually, I'm gonna reword this, not use delta. I'm gonna use delta. I'm gonna use that because it represents position. All right, if the change in position due to temperature when it's unrestrained equals some value, right?
Mm.
And then this wall is gonna produce some reaction, which is gonna push it back,
Yeah.
all right? Now, if you sum those two together, what do you think the total deformation here is gonna be?
Negative?
Well, it's gonna be 0,
Oh.
because they have to equal and opposite each other,
Yeah.
because the reaction is stationary. So technically, when you're solving the problems, you're supposed to set a negative sign, which is what I should have really explained last time. It's just I didn't, and I was just hoping you guys would understand that an increase in temperature means compression, and a decrease in temperature means tension. But if you want to see it in a more mathematical perspective, this is it. All right.
All right.
Do you want this for the formula sheet? Yeah.
I just have a quick question on the,
Sure.
Yeah. Did you find the force?
Yeah, to find the force,
Yeah.
that's acting for what?
How much it would deform if it was unrestrained? Yeah, because this support is gonna push it back, which then is gonna generate a force, alright? So if you were to release that support, it's gonna deform. because of the temperature. So that's what you're doing there. Yeah, and then you set this value equal to negative delta F right there, which is just gonna be the deformation due to the reaction. The unknown would be your reaction, but you have now delta is equal to PL over PA, where P is the only unknown. Does that make sense? Write out your deformation due to a force being applied on the structure.
Yeah.
Do you remember that?
And then
It's
From,
that,
this was
it's that,
it's the NL over EA.
That's just.
Yeah, you remember that? P and N are the same thing. P is just a general force, N is like the internal. Yeah. For this one, it's a singular bar, but it would just be whatever the total deformation is due to the force change.
So it was crazy, bro. Like the San Antonio.
And then
No way, you got the
that
same.
has to
So
equal this, but opposite direction.
You did
To
something
cancel
wrong
out,
with
make sure
that.
that the deformation is
so
zero.
serious.
that's why we're changing this.
There's no way it should not be the
Exactly.
same.
Okay. And then it would just be rearranging it to
Yeah.
say the.
Now, if you had two of these members, it's not as simple as this. It would be this for one member plus that for another member is equal to whatever the
So-
deformation, total deformation due to the temperature for each rod. Does that make
Somehow,
sense?
I don't know how that happened.
Yeah, because it's just one rod.
It would be the cross-sectional area, not this area. Yeah,
Yeah,
no,
on the
just
right
because
track.
it's supposed to be,
Yeah.
displacement.
The area would be, actually the area would just be one square.
Yeah, that's what I was asking, like, I'm not sure.
The length is 24 inches. You have the area and the elastic modulus. The only thing you need to find is that value P, which is your internal force in the rotor. And then that is what's defined by lateral strength.
Define E1, and put the stress over
Okay.
the.
So what do you do after you find the force then?
After finding the force,
Let me see.
I got
you tell me.
that.
So you would find.
Did you find the force?
I did.
What did you get for it?
Do I do this?
I got that negative 18.85 inclination.
Okay. Now,
I don't know if that's right, but.
well, you at least determined it was compression, right? Now, that compression, it can't move laterally, right? So that's why there's no epsilon x, because there's no strain in the length direction.
Yeah.
But there are strains in y and z.
Mm-hmm.
How would you do that? Well, I guess there would be a strain in the x direction. Let me rephrase that, actually.
There definitely would be.
You're right. Because otherwise it wouldn't make sense.
Unless we're doing the buckling stuff for something like, well,
Yeah, you would need to find epsilon x,
So
which,
just like before, basically.
yeah, it's the same process.
Okay, that's what I know.
So it's still
No, hold on. Let me see. I think I'm good.
Come here.
Z is the horizontal in this cross section, which would technically be into and out of the screen here. It's not, it's kind of hard to see. You're basically looking at an isometric view, but in 2D
Where did I
plans.
get that?
This is like the side view, this is the front view.
Wait, no.
Oh, I used the wrong, I used the coefficient instead of the.
You gotta think back now to DRF 1. Was that the course that Natalie Newman taught with the isometrics? Yes.
Yeah,
So
that's.
does it not just put into the two, and so half this force is.
Yeah, I just put in.
Wait,
Yeah,
well-
that's cool.
A lot confused.
That's what I'm picturing.
No.
Here, I will do this.
Did you,
Why is it EX?
cause I accidentally said it instead of
No. This? Oh, okay.
The y is pointing up, no matter what, it's just the x is in that length. Yes. You got the force right.
I guess.
One.
It looks like you did it right.
Could you
Why
do
do you
that?
The only
want-
thing is that force and tension or compression. Make sure to note that.
Oh, right, I forgot the.
Yeah, because when you're determining the lateral strains for this problem, it's really important to note that,
Okay.
because that messes up everything.
Okay, and then, no,
Z is
this,
one.
I don't know why I thought like,
Y is
because
one.
it's
X
equal.
is funny.
Well, that's right, either way, like, I mean,
Yeah.
this is the temperature
Is that
increase, so that
outside
assumption was right.
For each
Okay,
direction.
Like if this would be both sides,
Force.
it would be
Mhm.
minus pi
So you know how you
no,
work.
no, you wouldn't.
No, you don't.
No.
It would just be,
Yeah, because it would need to be an equilibrium.
right, cause if this was fixed, then this would,
Mhm.
What do we do?
this is how much, oh.
Right.
So we found
Oh.
this. Now, what do we do?
I have a question.
Yes.
So wait, would I
It
be
was
doing
this.
this, or would I be,
Times the
using
length.
these?
times.
You can use either or. This one is a more generalized one for three-dimensional
Yeah,
stresses.
'cause I was gonna say.
But
if you
how
use
many,
that,
how many,
We found that.
There's only one
But now we
force.
just.
one
put this
force, yeah.
five
In which
different
direction is that?
Forces, we put
That
it
force
over
is on
one now.
X.
It's in the X direction. So you can use either or, you'll get the same results.
So then y easy would just be zero then, right?
No, it's multiplied.
Not quite.
On the top, multiplied
Nope.
by the area.
To this.
That's what you gotta solve, remember. What is Poisson's ratio telling you?
Times
It's telling you the relationship of lateral strains to normal strains.
S.
Okay.
Yeah,
So you can use this equation.
Yeah, it's ST
You
times E times A.
Know what sigma x is, right? That's just gonna be force divided by the cross-sectional area.
Yeah, that one.
Is there any stress in the y direction?
18.85.
Right. Is there any stress in the z direction?
But
No. So you could just plug and chug the values for these equations here, and you'll get the same results.
But there would still be
One now.
obviously a z.
Yeah.
Yeah, the Poisson's ratio just stays there. It's built into the equation. The only thing that should ever change is the stresses in x, y, and z. Those are the things you need to consider.
So then we put the, so think.
Yep.
But then we'll find.
Real question.
Yes.
Then we put
So from here,
over.
what I
line
do
basis
is
elasticity.
exactly what I did like here.
Exactly.
0.6
Or
on the
You
side.
can use these equations here.
Yeah.
As long as you do both procedures correctly, you should get the same results.
So if I do this, that would just be what I got here
E.
for every,
This divided by the area, because remember, this is a force.
oh, yeah, yeah. that's-
Yeah,
So
And
that would
then-
just be
Wait, no.
that, and then sigma y and sigma z for everything is what?
There.
Would be divided by
What
their,
we're trying to find.
their own areas.
Yeah, but the only issue is there any stress applied in the x, in the y and z directions?
Is that not how you find it? You put it.
No, so what is the stress in those directions?
So it would be zero?
Yeah.
So it would just be, sorry, it would just be which direction?
The x
Or
direction.
the x?
So this is y, that should be x, and then,
Oh, my bad.
yeah, it's fine. And then just keep in
That's
mind
why I
the
was confused,
sun.
actually.
Oh,
Just
yeah.
keep in mind the sun.
Is that not
Is the
force?
force in tension or compression?
No, stress is force over area.
It would be,
Yes.
would it be going out?
So
Keep
to
going.
find the EX.
Increase in
it would
temperature.
be
What do you think would happen to the bar? Would it squeeze or would it stretch?
Over.
It'd stretch.
It would stretch?
No, I was close.
Is this right?
Tension or compression?
It goes from this, that way.
I don't know if you have to.
It's expanding that way, but it's restrained going that way. So what,
And then I want to-
the force would go down.
No,
Compression.
So it's negative.
Mhm.
So this is negative.
That's negative. And just keep in mind, is this force or stress?
Because we were talking.
So you need to find the stress.
So.
No, you just take that force divided by the cross-sectional area,
But
which
we're not-
conveniently happens to be 1/square root of
No, it is.
Oh, it's the same, 8
Yeah, they're the same in value.
Just like,
Okay.
there's no force.
But that's just an important note, it's just,
Zero.
it's the stress.
Wait, where does the
Same
water,
thing as the other two.
when I divided, do I put the one up here? or
But
down?
It's always in now, it's force
Yeah,
over
it's
area.
For
That's what I said.
Oh,
the stress in the.
and now I do this?
If you do it.
Yeah, and you just plug in sigma x, sigma y, find the sigma z. Is there any stress in the y or z directions from applied forces or restraint?
No, I'll do it.
No, it's free to move outwards, so you just set sigma y and sigma z equals 0, and then just plug and chug.
What's the elasticity of this thing? Yeah, it's only like that, so we'll feed that number over.
No, if you look.
Did you guys figure it out?
No, we just know.
If you look at
All right.
before what we did, we put.
Everyone here at least got a force of 18.85 kips, right? Everyone got 18.85 kips.
Yes.
So P is 18.85. So I'm not even going to show the steps to get that because everyone seemed to get it. All right? What we need to do is calculate the stresses in the x direction. How do we get that? 18.85 kips over 1 square inch. Keep in mind, it's a compression force. The temperature increase is going to cause the bars to compress. So the stress is 18.85 KSI. From there, we calculate the normal strain. This is equal to the negative 18.85 KSI divided by the elastic modulus of 29,000 KSI. What you should get is an elastic modulus, is a strain of negative 6.5 times 10 to the negative 4. From there, you can compute epsilon y, which should equal epsilon z, because the lateral strains are direction independent. And even if you were kind of confused, the lateral deformations are going to be the same too, because it's 1 inch by 1 inch. So the lateral deformations, if I had asked you that, would be the same also. And this is just going to be negative 0.30 times negative 6.5 times 10 to the negative 4, which will give you positive 1.95 times 10 to the negative 4. Make sense? All right. Now, considering the time restraint, I am not going to have you guys solve both of these. I'm only going to have you guys solve. I'll hand it out and ask you guys which one you want to solve. All right, and that's the one that I'll look at. If you want to take it home and try and solve it and get it back to me, I will do that too.
Sorry, which one do you want us to solve?
I'm gonna take a vote on which one I want you guys to solve here in class, and then if you guys want to bring it home and try solving it yourselves, I will let you guys do that too. So, which of you wants to solve problem 1 right now? Olivia's on problem 1. Emily, 1, 2, 3, 4 people. How many people want to solve problem 2 right now?
I'm still thinking.
You're still thinking.
Give us a minute and then we'll come back to it.
All right.
Is number 2 number 2 is on his
So this one we're just gonna have to break.
I'll do it in office hours if you want me to. I'm not solving that.
I feel like one's kind of harder, isn't it?
If I do something at home, I'll come to office hours, so I know the
Okay.
answer, but I don't want to solve
The
both right
only thing
now.
with this one is
Oh wait, actually, I
I think
changed my
it's
mind.
2 different composites.
One's just the.
Yeah, no, I'll stick with one.
Raise your hand if you want to do problem 1. All right, everyone. I think everyone wants to do number 1.
Number 2 is so much easier, guys.
I'll let you guys do number 2, and everyone else can do number 1.
Okay, that's fine. Dude, we literally just.
Yeah, I was like,
You can if you wanted. Again, these assignments are not graded. They're just ways for you to.
Determine change of length of AP.
Just as long as I see that you guys did something, you guys can take it home and try and solve the other one too if you want. Just let me see it before you leave, so I know.
Easy.